December 7, 1941. Pearl Harbor burns. America enters World War II. Within 6 weeks, the United States military will face a crisis more devastating than any naval defeat, a crisis that threatens to paralyze every tank, truck, aircraft, and landing craft in the American arsenal. Japan has captured 97% of the world's natural rubber supply. Without rubber, the American war machine cannot move, cannot fly, cannot fight. Military planners estimate 18 months until complete operational collapse. The countdown has begun. What nobody knows is that the solution already exists, locked away in a laboratory notebook belonging to a chemist whose colleagues mocked his experiments as worthless, whose methods were dismissed as stupid, whose materials were considered industrial garbage. Dr. Waldo Semon had spent years heating and mixing a brittle, useless plastic that every other chemist had abandoned as hopeless. His supervisors told him to stop wasting time. His peers laughed at his persistence. But in 1926, Semon had accidentally created something that seemed impossible, a flexible, rubber-like material made from polyvinyl chloride, the most worthless substance in industrial chemistry. 15 years later, that stupid trick would save the Allied war effort. This is the story of how one chemist's refusal to accept failure, combined with American industrial capacity operating at levels that seemed superhuman, transformed a laughingstock experiment into the synthetic rubber program that kept millions of soldiers moving, fighting, and winning. It's a story about chemistry, desperation, and the moment when mocked innovation became the difference between victory and defeat. January 1942, Washington. The War Production Board convenes an emergency meeting. The statistics are catastrophic. The United States military requires 600,000 tons of rubber annually. Civilian consumption adds another 600,000 tons. America's strategic rubber reserve contains exactly 70,000 tons, a 6-week supply at wartime consumption rates. Japan controls the Dutch East Indies, Malaya, and French Indochina, the sources of 97% of natural rubber. The British hold Ceylon, producing the remaining 3%, barely enough for their own needs. Every military vehicle requires rubber. A single tank uses half a ton. A battleship needs 75 tons. A bomber requires half a ton, just for tires, hoses, and seals. The average military truck contains 300 individual rubber components. Without rubber, aircraft cannot fly. Landing gear tires, hydraulic seals, fuel line hoses, electrical insulation all require rubber. Ships cannot operate. Countless gaskets, seals, and vibration dampeners demand rubber. Soldiers cannot march. Boots need rubber soles. Artillery cannot fire. Recoil mechanisms use rubber buffers. The chairman of the Rubber Reserve Company delivers the assessment that silences the room. Gentlemen, we have exactly enough rubber to sustain military operations through April. After that, we face complete strategic paralysis. We cannot win this war without rubber. We cannot even fight this war without rubber. The solution seems obvious: produce synthetic rubber. But in 1942, synthetic rubber is a laboratory curiosity, not an industrial reality. Standard Oil and IG Farben had developed a process using butadiene and styrene to create Buna-S rubber, but American production in 1941 totaled exactly 8,000 tons. The military needs 600,000 tons annually. Scaling production 75-fold in months appears impossible. President Roosevelt issues Executive Order 9025, creating the Rubber Supply Agency with unlimited authority and funding. The goal is insane: build from nothing a synthetic rubber industry larger than America's entire pre-war rubber consumption, operational within 18 months. Wall Street analysts call it fantasy. Chemical engineers call it impossible. Roosevelt's response becomes legend. The experts said it couldn't be done. Find me people who don't know that. What the experts didn't know was that the foundation for synthetic rubber already existed, buried in research that everyone had dismissed, and that foundation had been poured by a chemist in Ohio who'd spent 15 years being laughed at for trying to make garbage flexible. Waldo Semon was born in 1898 in Demopolis, Alabama, growing up in poverty that made college seem impossible. But Semon possessed something transcending poverty, an obsessive curiosity about why materials behaved as they did. He won a scholarship to the University of Washington, earned his undergraduate degree in chemistry, then completed his doctorate in 1923, studying physical chemistry under renowned Professor Francis Rutten. B.F. Goodrich hired Semon immediately, assigning him to their research laboratory in Akron, Ohio. His initial projects involved improving rubber adhesives and developing new coating materials. The work was conventional, predictable, and boring. Semon wanted to create something entirely new. In 1925, Goodrich asked Semon to find a use for polyvinyl chloride, abbreviated PVC. This polymer had been discovered in 1872 by German chemist Eugen Baumann, who'd accidentally created it by leaving vinyl chloride exposed to sunlight. The resulting material was rigid, brittle, and apparently worthless. For 50 years, PVC had remained a chemical curiosity, interesting in theory, useless in practice. Every chemist who'd examined PVC reached the same conclusion: the material was too rigid for practical applications. Its brittleness made it impossible to form into useful shapes. It couldn't be molded, extruded, or fabricated. Industrial chemistry had moved on, pursuing more promising polymers, but Semon looked at PVC differently. If the material was too rigid, perhaps chemistry could make it flexible. The conventional wisdom said this was impossible. PVC's molecular structure locked its chains into rigid configurations. Heating PVC just degraded it. Adding solvents either dissolved it or had no effect. Semon tried anyway. He began a series of experiments that his colleagues openly mocked. He mixed PVC with various compounds, plasticizers, oils, resins, and subjected the mixtures to heat and pressure. The other chemists called it stupid. "You can't make PVC flexible," they told him. "You're wasting time on garbage chemistry." For 18 months, Semon failed repeatedly. PVC mixed with mineral oils remained brittle. PVC mixed with vegetable oils degraded into sludge. PVC mixed with various solvents either dissolved or stayed rigid. His supervisor suggested moving to more promising research. Semon requested 6 more months. Then, on one morning in 1926, Semon tried something different. He mixed PVC with tricresyl phosphate, a chemical normally used as a gasoline additive, and subjected the mixture to prolonged heating at carefully controlled temperatures. When he opened the reaction vessel, he found something that shouldn't exist: a flexible, rubber-like material that could be bent, twisted, and stretched without breaking. Semon had accidentally discovered plasticization, the process of inserting small molecules between polymer chains to allow them to slide past each other. The rigid PVC structure remained intact, but the plasticizer molecules acted as microscopic ball bearings, allowing flexibility while maintaining strength. His colleagues were unimpressed. "It's not real rubber," they pointed out correctly. "It's just flexible plastic. What's the application?" Semon didn't have a good answer. Flexible PVC wasn't quite rubber. It couldn't stretch as far, couldn't recover from deformation as completely. It seemed to exist in an awkward middle ground between rubber and plastic, not quite suitable for either application. Goodrich filed patents on Semon's discovery, but didn't pursue commercial development. The company was in the rubber business, and flexible PVC wasn't rubber. Semon continued his research, improving the plasticization process, experimenting with different plasticizers, and characterizing the material's properties. But flexible PVC remained a laboratory curiosity, interesting but useless. By 1940, Semon had spent 14 years studying a material nobody wanted. His career had stalled. Younger chemists passed him in promotions. His supervisor suggested transitioning to management. Semon kept experimenting with PVC. Then Japan captured Singapore on February 15, 1942. The rubber crisis transformed from theoretical to immediate. America needed synthetic rubber, needed it in quantities measured in hundreds of thousands of tons, needed it within months. The Rubber Reserve Company convened emergency meetings with every chemical company capable of large-scale production. Standard Oil presented their Buna S process, derived from German technology. DuPont offered neoprene, a synthetic they'd developed in the 1930s. Goodrich sent Dr. Waldo Semon, whose presentation on flexible PVC was met with skepticism. "Your material isn't rubber," procurement officers pointed out. "It doesn't have rubber's elasticity. It can't replace natural rubber in tires or most applications." Semon agreed. Flexible PVC isn't a rubber substitute for most applications, but it can replace rubber in many applications where flexibility matters more than elasticity. Electrical insulation, hoses, gaskets, boots, ponchos, and hundreds of other military items currently consuming scarce natural rubber. The procurement officers studied Semon's samples, flexible tubes, sheets, and molded objects that looked like rubber, felt like rubber, but weren't rubber. "Can you produce this at industrial scale?" they asked. "We've never tried," Semon admitted. "We have laboratory processes that work beautifully at small scale. Scaling to industrial production would require solving numerous engineering challenges." How long would scaling take? Semon calculated mentally. Conventional development would require 3 years minimum. Pilot plant, process optimization, engineering design, construction, testing. But these aren't conventional circumstances. Could you do it faster? Give me authority, funding, and freedom from normal oversight, and we'll find out. The contract arrived at Goodrich on March 20, 1942. Semon received unlimited funding, highest national priority for materials and equipment, and authority to commandeer any resources necessary. His mission: create industrial-scale production of flexible PVC within 6 months. The alternative was millions of soldiers without boots, aircraft without hoses, and vehicles without seals. Semon assembled a team of chemical engineers and began the most intense development program in plastics history. The challenges were immense. Laboratory processes that worked perfectly at 1-pound batches failed catastrophically at 1,000-pound batches. Temperature control became nightmarish. PVC degraded if heated too much, stayed rigid if heated too little. Mixing 1,000-pound batches required equipment that didn't exist. Semon solved problems through relentless experimentation. When commercial mixers couldn't handle PVC viscosity, he designed custom mixing equipment, fabricated in Goodrich's machine shops within weeks. When temperature control proved impossible in large vessels, he developed continuous processing where material flowed through temperature-controlled zones. When plasticizer distribution created inconsistent products, he invented new mixing methods using shear forces. By September 1942, Goodrich had operational pilot plants producing flexible PVC at rates exceeding 1 ton per day. Military inspectors tested the material exhaustively: temperature tolerance, chemical resistance, flexibility, durability. Flexible PVC passed every test for applications not requiring true rubber elasticity. The War Production Board ordered immediate full-scale production. By December 1942, 3 Goodrich plants were producing flexible PVC around the clock. By March 1943, production exceeded 10,000 tons monthly. By June, 20,000 tons. The material flowed into military supply chains: electrical insulation for aircraft, fuel hoses for vehicles, ponchos for soldiers, gaskets for equipment, and boots for infantry. But flexible PVC was only one piece of the synthetic rubber solution. True rubber replacement required Buna-S, and that program faced even more daunting challenges. The Buna-S synthesis required butadiene derived from petroleum and styrene from ethylbenzene. In 1941, America produced virtually none of either chemical at the scales required. The rubber program became the largest industrial mobilization in history. The government financed construction of 51 synthetic rubber plants, 15 butadiene plants, and 29 styrene plants. Total investment exceeded $700 million, equivalent to over $12 billion today. Construction timelines that normally required 3 years were compressed to 8 months. Plants designed on Monday were under construction by Friday and producing rubber by the following spring. Standard Oil's Buna-S process became the backbone of American synthetic rubber production. The chemistry was straightforward: butadiene and styrene mixed in a 3-to-1 ratio, polymerized using free radical initiators at controlled temperatures. But scaling to industrial production required solving thousands of engineering challenges. Butadiene production required cracking petroleum at precisely controlled temperatures. Too cool, the yield dropped. Too hot, the butadiene degraded. The catalysts required exotic metals, chromium, aluminum oxide, available only in limited quantities. Purification demanded fractional distillation towers operating at extremely precise temperatures. Styrene production started with ethylbenzene, created by reacting ethylene with benzene. The ethylbenzene was then dehydrogenated, hydrogen atoms stripped away, creating styrene. This process required temperatures exceeding 1,000 degrees Fahrenheit, specialized catalysts, and extremely pure feedstocks. The polymerization itself demanded obsessive control. Temperature variations of 5 degrees ruined entire batches. Contamination by oxygen stopped polymerization. Excessive initiator created degraded rubber. Insufficient initiator left unreacted monomers. American chemical engineers solved every problem through brute force experimentation. When catalyst supplies ran short, they developed alternative catalysts. When temperature control failed, they designed better control systems. When contamination caused failures, they built cleaner facilities. When they needed 5 times more chemical engineers than existed in America, they trained petroleum engineers, mechanical engineers, and even bright high school graduates in crash courses lasting weeks. By late 1943, American synthetic rubber production exceeded 100,000 tons monthly. By spring 1944, production surpassed natural rubber consumption from before the war. The impossible had become routine. The rubber program succeeded through American industrial capacity, operating at levels that seemed miraculous. Factories appeared in months where factories hadn't existed. Chemical plants producing exotic materials at scales never attempted began operations within a year of breaking ground. Trained workers materialized through emergency training programs that compressed years of education into weeks of intensive instruction. Dr. Waldo Semon's flexible PVC became a critical component of this success. While true synthetic rubber replaced natural rubber in tires and elastic applications, flexible PVC replaced rubber in thousands of military items where flexibility mattered more than elasticity. Electrical insulation, hoses, gaskets, ponchos, tents, boots, gloves, medical equipment, communication wire insulation. The list extended across hundreds of categories. By war's end, American production of flexible PVC exceeded 200,000 tons annually. The material Siemens colleagues had mocked as worthless garbage had become an essential component of military supply chains. The stupid trick of mixing and heating PVC had created an entirely new class of materials that continues dominating modern life. Vinyl floors, plastic pipes, insulated wires, and countless consumer products trace their origins to Siemens' refusal to accept that rigid polymers must stay rigid. The broader synthetic rubber program produced over 820,000 tons in 1945, more than America's total pre-war rubber consumption. The program employed over 70,000 workers, consumed enormous quantities of petroleum and chemicals, and represented industrial mobilization so vast it seemed impossible until accomplished. After the war, Semon received the American Chemical Society's highest honors for his PVC plasticization work, but characteristically, he remained focused on research rather than recognition. He held over 115 patents across diverse fields: rubber chemistry, plastics, adhesives, and coatings. He continued working at Goodrich until retiring in 1963. Still experimenting with new materials, still pursuing ideas others dismissed. In a 1970 interview, Semon reflected on his career. "People ask why I kept working on PVC when everyone said it was worthless. The answer is simple. I believed the material had potential that others couldn't see." Sometimes in science, the most important discoveries come from refusing to accept conventional wisdom. My colleagues thought I was stupid for heating and mixing garbage plastic. Maybe I was stupid, but stupid persistence created something useful. The interviewer pressed further. "Did you realize PVC would become so important?" Semon smiled. "In 1926, I thought I'd created an interesting laboratory curiosity. In 1942, I realized it might save lives. By 1945, it had become clear that flexible PVC would transform modern manufacturing. But even then, I couldn't have predicted how thoroughly vinyl materials would dominate modern life. Sometimes you create something whose full implications only emerge decades later." Today, global PVC production exceeds 40 million tons annually. The material exists in pipes, medical equipment, construction materials, automotive parts, and thousands of consumer products. Every vinyl record, every plastic credit card, every insulated electrical wire traces its lineage back to Siemens' stupid trick, mixing plasticizers with worthless rigid polymer and applying heat. The synthetic rubber program stands as testament to American industrial capacity mobilized under crisis. In 3 years, America created from nothing a chemical industry larger than its pre-war rubber consumption, developed new materials and processes, trained tens of thousands of workers, built dozens of enormous facilities, and produced rubber at scales that supplied not just American needs, but Allied requirements. The program cost $700 million but saved the war effort. Without synthetic rubber, Allied victory would have been impossible. Tanks would have sat immobile for lack of treads. Aircraft would have been grounded for lack of tires. Ships would have been paralyzed for lack of seals. Soldiers would have marched in inadequate boots. The entire Allied military machine depended on rubber, and synthetic rubber kept it moving. Dr. Waldo Semon died in 1999 at age 100, having witnessed his laboratory curiosity transform into an essential component of modern civilization. His obituaries noted his technical achievements, his patents, his honors, but perhaps his most important legacy was demonstrating that persistence matters, that dismissed ideas sometimes contain hidden value, and that stupid tricks occasionally change the world. In the end, millions of American soldiers won their battles because one chemist refused to give up on an idea everyone laughed at. They advanced across Europe in boots with synthetic soles, rode in vehicles with synthetic seals and hoses, used equipment insulated with flexible vinyl, and were supplied by a logistics system that ran on synthetic rubber. They won because Waldo Semon had been too stubborn to accept that rigid plastic must stay rigid, too persistent to abandon worthless materials, and too focused on potential to care about mockery. The stupid trick of heating and mixing garbage plastic had saved the Allied war effort. Sometimes the most important innovations come from people who don't know their ideas are supposed to be impossible. Sometimes persistence matters more than brilliance. And sometimes the material everyone dismisses as worthless becomes the foundation of victory.